The foundation of quantum mechanics is explained by the following experiment. Suppose we have a wall with 2 holes. Suppose we shoot marbles at it, 1 marble at a time. Behind the wall, we have a cloth. Each time a marble hits the cloth, we mark where it landed. As marbles hit the cloth in the same spot more than once, we mark the red mark darker. Some marbles make it through the holes by bouncing off at an angle. But most marbles that make it through the holes continue in a straight line. After a while, there will be many red marks on the cloth. The darkest red marks will be directly behind the 2 holes. Now suppose the 2 holes are very narrow. Suppose the marble is very small. Now the result is very different. A striped pattern is produced. The marbles never hit the cloth in the areas between the stripes. All particles in the universe produce this striped pattern, provided that both they and the holes are small enough. No matter how many times we repeat this experiment, and no matter what type of object we use to replace the marbles, the result is always the same. Only one known phenomena can explain this result. Waves. When a wave passes through a hole, it spreads out on the other side. If there are 2 holes, 2 waves are produced. When you have 2 waves, they interact with one another. In some areas they strengthen each other, and in other areas they cancel each other out. This creates a striped pattern. This is the exact same pattern that we saw before. This means that all objects really behave like waves. But if all objects behave like waves, then why don't we see a striped pattern for the large marbles? Large objects have much more energy than small objects. Waves have more energy by having a higher frequency. When waves with higher frequencies interact with one another, the pattern is different. Large objects have more energy, and they therefore behave like high-frequency waves. This is why large objects do not produce a striped pattern, but small objects do. But there's still a problem. For a wave to produce a striped pattern, each wave must simultaneously pass through both holes, so that there will be two new waves that interact with one another. But we're shooting the marbles at the wall only one marble at a time. This means that each marble must somehow simultaneously pass through both holes in order to create the striped pattern. Let's see if this is what actually happens by blocking one of the holes. The striped pattern disappears. Most of the marks are now directly behind the one open hole. Now let's block the other hole instead. Again, the darkest lines are directly behind the one open hole. But if we unblock both holes, the striped pattern returns. Areas that were hit many times when one of the holes was blocked are now never hit when both holes are open. This means that each marble really does have to simultaneously pass through both holes to produce a striped pattern. Let's test this by putting a detector in front of each hole. We should expect that both detectors will simultaneously indicate that the marble passes through it. However, this is not what happens. Each marble only passes through one detector or the other, but never both. Also, once we place detectors in front of the holes, the striped pattern disappears. Now the darkest lines are directly behind the two holes, just as when we blocked one hole at a time. Let's try putting a detector in front of only one of the two holes. It turns out that having even just one detector has the same effect as having two detectors and causes the stripe pattern to disappear. Any attempt to discover which of the two holes the marble passes through forces the marble to pass through one hole or the other, and not both. One detector has the same effect as two because once we know if the marble passed through one hole, then we also automatically know whether or not it passed through the other one. A marble goes through both holes only when we are not trying to find out which hole it went through. But when we do try to find out, the marble goes through only one hole or the other. So what if we place detectors in front of both holes and just close our eyes and not look? We don't know for sure what is happening when we are not looking, but we do know what the mathematics describing the waves tells us. When waves pass through a detector, the waves are altered so that they can no longer interact with one another. This means that the striped pattern will disappear even if we are not watching it. The detectors will cause this to happen on their own. However, the mathematics also says that each wave still simultaneously passes through both holes, even with the detectors present. But when we open our eyes and look, we always see the detector indicating that the marble passed through only one hole or the other, and never both. Each wave still simultaneously passes through both holes, even with the detectors present. But when we open our eyes and look, we always see the detector indicating that the marble passed through only one hole or the other, and never both. This means that the marble must be more than just a wave. The wave only describes the probability of where we will see the marble when we look at it. The probability of the marble being at a particular location is given by the wave's amplitude. The higher the amplitude of the wave at a particular location, the higher the probability is that we will see the marble there when we look. This means that we can never simultaneously know both the position and the momentum. Before the wave hits the detector, we know exactly what direction the momentum is in. However, we know nothing about the object's position. Immediately after we see the marble hit the detector, we know exactly where its position is, but now we know nothing about the direction of the momentum. Not only are we not able to simultaneously measure the position and momentum of an object, the object does not even have a specific position or momentum until we observe it. If the marble always had a specific position, then the marble would not be able to go through both holes simultaneously, which is necessary to produce the striped pattern. But if all objects are just a wave of probability until we observe them, then this means that the detectors and all the objects the marbles interact with are just a wave of probability too. Suppose we place an object behind each of the two holes. The marble will knock down one of the two objects, depending on which hole it passes through. If we close our eyes and don't look, then the wave of probability passes through both holes, and each object being knocked down also becomes a wave of probability. Just as each marble simultaneously passes through both holes, each object is now simultaneously both standing up and knocked down. No matter how long we wait after the marbles have hit the objects, each object will continue to have a probability of still being in the standing position. And each object will also continue to have a probability of being in the knocked-down position. According to the mathematics describing the probability waves, neither outcome is certain. It's only when we open our eyes and look that we see only one outcome or the other. It's not just that we ourselves do not know the outcome until we look. It seems that even the universe itself does not know which object is standing up and which object is knocked down until we actually open our eyes and observe the results. To explain why this is the case and what this means about the fundamental nature of our universe, let us talk about spin. The direction of the spin of a particle can be described by an imaginary arrow. Particles spinning in opposite directions will have their arrows pointing in opposite directions. particles are too small to see the spin directly with our eyes, but we can build detectors which tell us if the spin is in the direction of the red plate or if the spin is in the direction of the blue plate. Suppose we think that we already know the spin of a particle ahead of time, because we have measured it previously and we line up the detector with this direction. The detector will always give us the same result we measured previously. But if the spin we measured previously is not in the same direction as the detector, then the act of measuring the spin ends up changing it. It is not possible to simultaneously measure the spin of a particle in more than one direction at a time. If we want to know the direction of the spin in the horizontal direction, then we need to rotate the detector. But why does this mean that the universe does not know what an object is doing until we observe it? The answer lies in the fact that we can produce pairs of particles that always spin in opposite directions. If the two detectors are aligned in the same direction, then when the spin of one particle is measured to be towards the red plate, the spin of its partner is always measured to be towards the blue plate. This is true 100% of the time. This is still true the vast majority of the time, even if we offset the detectors by 45 degrees. We know this based on experiment. If we offset the detectors by 45 degrees, then when the spin of one particle is towards the red plate, the spin of its partner will be towards the blue plate, the vast majority of the time. Suppose the two detectors are perfectly aligned with each other, and they are both in the diagonal position. Does the universe know ahead of time that the first particle will be measured to be towards the red plate, and that the spin of the second particle will therefore be towards the blue plate? If the universe knows ahead of time that the spin of the second particle will be towards the blue plate, then this means that the universe must know that the spin of the first particle will probably be towards the red plate, even if we rotate its detector by 45 degrees, either into the vertical position or into the horizontal position. Therefore, if the universe knows the results in the diagonal observation ahead of time, then the universe would also know that if one detector will be rotated into the vertical position, and the other detector will be rotated into the horizontal position, the two particles will still probably be spinning in opposite directions. But when we actually do the experiment, this isn't what happens. When the two detectors are offset by 90 degrees, there is no correlation between the measured spins of the two particles. When the two detectors are offset by 90 degrees, the spins of two particles are just as likely to read in the same direction as they are to read in opposite directions. Therefore, if we start out by assuming that the universe knows ahead of time what the measurements will be, this leads to a contradiction. Assuming that the universe knows the answers ahead of time implies that most of the time, the measured vertical spin of one particle must be in the opposite direction of the measured horizontal spin of the second particle. But we know that this is not the case. The apparent implication is that the universe cannot know ahead of time what the measurement of the spin will be, and the universe makes up its mind only when the spin is actually observed. The apparent implication is also that when the spin of one particle is measured, it sends an instantaneous message to its partner to spin in the opposite direction. If each particle makes up its mind about what direction it's spinning only when it's observed, then we need this instantaneous message from one particle to the other in order to guarantee that the two particles will always decide to spin in opposite directions when the detectors are aligned. This is true no matter how far apart the two particles have traveled away from each other. Even if we wait until the two particles are on opposite sides of the universe before we make our observation, this instantaneous message still seems to occur. Until we observe the particles, their spins are nothing more than probabilities. But we need to observe only one of the two particles for both of them to simultaneously decide in what direction to spin. If everything in the universe is made out of these particles, including the detectors themselves, then the detectors are also nothing more than a probability until they are observed. According to the mathematics describing the probabilities of the particles, passing through the detector is not what causes the particle's spin to decide to spin in one direction or the other. Passing through the detector entangles the detector to the particle, in the same way that the two particles are entangled to each other. The moment we look at the detector, it seems to send an instantaneous message to the particle, so that the detector's measurement will agree with the spin of the particle. This is the same way in which the two particles seem to send instantaneous messages to each other. There are many possible explanations as to what's actually happening and how to interpret these results, and this is a matter of considerable debate. But if we really do have these types of instantaneous messages, which are faster even than the speed of light, then this creates an interesting situation with Einstein's theory of relativity. According to Einstein's theory of relativity, different observers will disagree about which of two events happened first, and no observer is more correct than any other. From one observer's point of view, the right particle was observed first and caused the left particle to change its spin. From another observer's point of view, the left particle was observed first and caused the right particle to change its spin. Therefore, we can't know which of these events is the cause and which of these is the effect, since both points of view are equally valid. In fact, according to quantum mechanics, we can't even know which particle is which. Suppose we have two particles in a container. Each particle does not have its own separate probability wave. There is only one probability wave, which describes the probability of measuring the two particles in every possible combination of positions. The probability that particle 1 will be in one position and that particle 2 will be in another position is exactly equal to the probability that the two particles will be in the swapped positions. Therefore, we cannot know if a particle we're observing is the same particle we measured earlier. If we think of our container as the entire universe, then this would imply that the universe consists of just one probability wave, governing the probability of all the particles in existence. But if we ourselves are made out of these exact same particles, then why is the act of us observing something so fundamentally different from everything else?